Okay, well, previously we saw that the weight times x bar, so the total weight of something times x bar distance, was equal to the sum of x bars of all the smaller areas. So if we look at a situation like that, then we can take the left-hand side and we could take the limit as w approach 0 of the sum of x tilde w. And that, of course, is going to equal the integral of x tilde dw. So from this idea, we can then develop the idea that and I could represent then x bar as this integral over the total weight, which would be the integral of all these differential weights, integral dw. So likewise, I could find y bar is integral y tilde dw over the integral dw, and z bar, if we wanted it, equals the integral of z tilde dw over the integral of dw. So in general, the above relationships for a 3D body they result from essentially a moment balance of the body's weight, make it a big W, applied here at the CG, center of gravity, CG. So we can have an X bar there, a Y bar there, and a Z bar up to the center of gravity there. So it's a moment balance of this W about the X, Y, and Z axes. And we can equate this then to a differential element here with weight dw. And each of these elements then is what we're summing. And each of these have individual x tildes, y tildes, and z tildes. So it's the same thing we did with summations, only now we're extending it to integrals. So in this way, we can also broaden this out for other calculations like the center of mass, where dw is going to equal some constant gravity times dm, where if g is constant, we'll be able to divide it out just like we did in the summations, and we can end up with an x bar equals the integral of the x tilde g dm instead of w over the integral of g dm, and you can see that we can divide out g here. So this is just the integral of x tilde dm over the integral of dm, and likewise y bar equals and z bar equals the integral of y tilde dm over dm and the integral of z tilde dm over dm. So that's for center of mass. Then for centroid of volumes, we know that dm equals rho times dv, and if our density here equals constant, we can divide that out and we'll end up with an x bar equals the integral over the volume of x tilde dv over the integral over the volume of dv, and y bar equals the integral of y tilde dv over the integral, and this is over the volume of the integral over the total volume, and z bar equals the integral over the volume of z tilde dv over the integral over the volume of dv. So let's actually do an example of this guy. So here we have an irregular shape with the top line being f of x equals x squared, and it's bounded by y equals 1 over here, the line y equals 1, and the x-axis. So I want to find x bar. So to do this, we always do these things in the same way. Probably the best way to do this is, if I'm looking for x bar, first thing I need to do is I need to settle on a dx or differential element and then see what we're doing here. So I create this rectangle with the width being the differential element size and the height here being some f of x value defined by this function. That way here we have some x to the center, top center of that thing, and we can stick that x value in f of x and find out what this is. So if I was going to set that up, let's first do the area. The area equals, I like to do the area first because then I know I can set my integral up properly. So I'm going to go from 0 to 1 as the bounds of this, and I am essentially going to take the integral of this top function and subtract it off of the integral. It's kind of trivial, the integral of y equals 0. So that's essentially going to end up with 0 dx, or minus the integral from 0 to 1 of f of x dx. Or actually, I got that backwards. We got to take the top line and subtract the bottom line. So we're going to take f of x and subtract off 0. So the reason I'm doing this is because you'll see when we do y bar that we'll use the same approach, the same logic. So I'm taking this area and I'm just subtracting off a 0 area. So most of the time we just skip the second part. But anyways, the integral is 0 to 1 of f of x dx is what we're going to solve here. And this equals the integral from 0 to 1. Well, f of x is equal to x squared, so I write this as a function of x, and I can do this integration pretty simply then. So this equals x cubed over 3 evaluated from 0 to 1 for our definite integral, which equals 1/3, or 1 cubed is 1 over 3, minus 0 over 3, which is just 1/3. So that's our distance for x bar on this. Well, it's a distance. That's our area. That's not our x bar distance yet. So if we want to solve for x bar, we have to throw this into the formula. So now I'm going to add an x to this. So x, not add, but multiply in here by x, because that's the distance x tilde there of essentially x squared dx. And this is all over the a again, so I can just write 1/3, or actually I'll write the integral here and then we'll do it. The integral of x squared dx. So this is from 0 to 1, and this is also from 0 to 1. So we know this is 1/3 down here because we already calculated from above. So up top here, we're going to have x cubed dx. So that's going to be x to the 4 over 4 evaluated from 0 to 1 equals 1/4 over 3/4. 1/4 over 1/3. What did I say? 3/4. The area is 1/3 here. So this is the same thing as then 3 over 4. And that equals our x bar. Let's use this ink to shape routine. So now for y bar, what we want to do is find our dy. And dy is like this, which means we're going to need to do this, break this into two parts essentially. What we'll do is we'll find, when we're working on the area, we'll start with the area first. We'll take the area of this square and then subtract it from the area here to get our y bar. So the area equals from 0 to 1 of 1, and this has a height of 1, dy minus the integral from 0 to 1 of f of y dy. So this is going to be this rectangle minus this shape here. And let me get rid of. So we'll take this shape and we'll subtract this shape out, and what we're left with is our answer, this shape. And I should get the same area of 1/3 that I got up here. Well, if f of x equals x squared equals y over here, then x equals the square root of y, and this is f of y. So this equals the integral of 1 minus f of y dy, and then this equals the integral of 1 minus y to the 1/2 dy, which is y minus 3y to the 3/2 over 2 evaluated from 0 to 1. And this in fact does equal 1/3. So calculating y bar, then we get this function, then that simply integrates to this, and we end up with 1/10 over 1/3, which is 3/10.